Let me just check to make sure it's not all wonky. Good enough? All right. So we left off last time talking about the three major energy sources for our muscle cells. And we're picking up today with some different types of contractions. So we've talked in general just about what a contraction is and this concept of a power stroke, right? But different times our muscles can contract differently. In other words, not all contractions are the same. So a muscle twitch is when a very small percentage of the muscle fibers in a muscle group are actually contracting. Or maybe it's just part of the muscle that's contracting, and it's not contracting down the entire length of the muscle. You know what a twitch is because you've had a twitch before. Have you ever had that eye twitch and you feel like the whole world can see your eye going like this, right? But really no one notices. I had it earlier today, actually. So a twitch is just either a part of the muscle fiber that's contracting or just very few muscle fibers in an entire muscle group that are contracting. And there's three phases on what's called a myogram. So a myogram is a graph of muscular activity. It's how we measure muscle contractions. You measure muscle contractions on a myogram, and there's three phases. One's called the latent period. So the latent period is this kind of anticipatory time between when the action potential gets there and when that action potential travels to the muscle cell. So it's kind of this like waiting period. You know it's coming, but it's just not here yet, right? The signal has been sent, but it hasn't been transmitted to the muscle fiber yet. The contraction period is when, now that excitation has traveled into the muscle cell and now it's contracting. We have this cross bridges forming, the power strokes happening. And then the relaxation period is when everything goes back to normal, right? Calcium reuptake into the SR, cross bridges detaching, active sites being blocked, right? And so a muscle twitch is the smallest piece of that. There's something called a refractory period that's important here because a refractory period is the time between one muscle contraction and the next one. And this refractory period is important because if it's not there, if it's not recognized, then more powerful or more dangerous muscle contractions could result. So a muscle fiber during a refractory period is typically unable to respond to another stimulus, right? It's kind of like you already have all these things you're juggling, right? You have all of these assignments, you have an exam on Tuesday, and I'm saying, and here's something else. And you're like, no, please stop, right? That's the refractory period. You've met a refractory period and you can't take any more. The muscle cell needs time to reset and reestablish before it can do anything else. Cardiac and smooth muscle have a refractory period also, but they're a lot longer. The refractory periods are a lot longer than a skeletal muscle refractory period. A cardiac and a smooth muscle, those have to relax fully and completely before they can contract again, whereas a skeletal muscle only has to partially relax. And so this can lead up to several different types of contractions, like I'm kind of leading into now. So this is that myogram, right? So we have this latent period, this kind of time that it takes that information, that electrical signal to build and to get to our muscle fiber. Then we have the cross bridges forming, tension building, the shortening, right? And then the relaxation phase. The refractory period is the time during that relaxation phase that another stimulus can't tell it what to do. It will ignore another stimulus. And so for cardiac and smooth muscle, that refractory period is a lot longer than it is for skeletal muscle, and we'll see why. Make sure I didn't skip anything. Okay, so the tension that's produced during a muscle twitch is going to vary. It's going to depend on the timing and frequency of how much it's being stimulated, right? Contract, 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 right? If it's being told to contract over and over and over again, it can build up a lot of tension, right? As just compared to like one or two little signals, right? Also the length of the fiber. How big is this muscle fiber? And what type of muscle fiber is being stimulated here? We haven't talked about muscle fiber types. We'll get there. But not all muscle fiber types are the same. So not all twitches are the same. And you know this because you've probably had a twitch in your eye and you've probably had a twitch in your calf muscle. And the twitch in your calf muscle feels awful like a Charlie horse. instead of just a nice little annoying twitch in your eye. And the difference is the types of muscle fibers. So one of the ways tension can build is something called wave summation. So with wave summation, you have a signal coming in and there's some tension. But before the muscle can completely relax, there's another signal that's coming in. And so more tension builds. And then another signal comes in and more tension builds. And so the tension continues building and building and building because the muscle is continually being stimulated over and over again. It's like waves pounding on the beach, right? That's why it's called wave summation. It's happening over and over and over again. And so there's progressively greater tension as time goes on with wave summation. What's happening at the cellular level is the sarcoplasmic reticulum isn't able to bring in and reset all of those calcium ions. So in other words, some of the calcium stays floating around in the cytosol of our muscle cell, which means some of our actin remain contacted and bound to myosin, which means our muscle doesn't really get to relax, right? If calcium's still out there, our muscle isn't able to relax. So the amount of calcium is going to increase with each stimulation. And with more calcium going out into that cytosol, more active sites can be revealed, more myosin heads can bind, more cross bridges can form, more power strokes can happen, more tension can build. So wave summation is pounding these currents, this action potential over and over and over again to build more and more tension. So tension depends on the frequency of those impulses, right? So if that impulse is coming at a fairly slow pace, tension won't build that quickly. But if the impulse is coming very, very quickly, we could reach a point called unfused tetanus. So wave summation happens, and then unfused tetanus can happen. Unfused tetanus is when the fibers are stimulated about 50 times per second. Bam, 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 right? 50 times per second. It's hecka fast, right? The fiber can partially relax, but then it contracts it. Partially relax. There's really no time for it to reestablish relaxation at all. So the tension kind of pulsates. The tension kind of pulsates. Your muscle fiber produces about 80% of its maximum tension with unfused tetanus. This is not a Charlie horse, but this is a cramp. You would feel this as a cramp. Fused tetanus, this is the Charlie horse. This is the dangerous one, right? The fiber stimulated even more, 80 to 100 times per second. I'll tell you right now, I'm not going to ask you how many times per second. I'm not a numbers person. There are some numbers you'll need to know eventually. This is not one of them, so don't get wrapped up in the numbers. So it's just stimulated a lot, right? The muscle does not get to relax at all. So it stays at maximum tension, right? And you know what that feels like if you've ever had that muscle cramp. And you're like, right? It hurts really bad. So depending on where in your body is being affected by this tetanus, right, you could have to go to the hospital, right? If it's a cramp or tetanus in the intercostal muscles of your ribs and your ribs aren't able to expand to inflate your lungs, then you can't breathe, right? All of this, the tetanus, the wave summation, is all related back to that refractory period. Because the skeletal muscle can be stimulated to contract before it's completely relaxed, it's going to build maximum tension. How does the refractory period of cardiac and smooth muscle compare to the refractory period of skeletal muscle? It's longer. The refractory period in cardiac and smooth muscle is longer, which means you're less likely to have wave summation and tetanus. Thank goodness. I don't want my heart to cramp up, right? I don't want my stomach all the way up, my stomach or my intestines to be in tetanus. That would be horrible. You wouldn't be able to move food. Your heart wouldn't be beating, or it would be beating and stay contracted. That would not be good for your body, right? So those muscle cells are specialized, and we'll talk about how they're specialized in a little bit, but they're specialized to not take in any impulses until they've completely relaxed, and then they can take another one. So this is just a look graphically at the myograms of these different things, right? So we have unfused tetanus wave summation. So wave summation is just the idea that the tension's building. Unfused tetanus means that it reaches that maximum tension, but there's a little bit of break, so it pulses kind of at maximum tension. Fused tetanus is where you're stuck. Lockjaw. Ugh. I can't open my mouth, right? That's another example of fused tetanus. So there is a length-tension relationship in the sarcomere, so and in our muscle fibers. So this has to do with there being an optimal length of a sarcomere. Our sarcomere has, we just kind of draw out, right? Thin M line. Actually, I won't even draw the M line. I'll just draw more thin. Another Z line, and then thick. Okay, notice how I drew this, right? There's a little bit of overlap, but there's also a little bit of space where there's no thick filaments, right? And a little bit of space where there's no thin filaments. So imagine the sarcomere. I'll be a little more precise now. Here's my Z lines. Here's my thin filaments. Imagine that this was my resting sarcomere. What's the difference? If this is short. Yeah, it's already short. I mean, if this thing contracts, right? Remember, the sarcomere shortens and the thin filaments pull between the M line. The Z lines go together. There's not a whole lot of room for movement there, right? Or what if the sarcomere was like this? What's wrong with that one?
There's a lot of space.
There's too much space. Is there any overlap?
No.
Almost none. So how are the myosin heads going to connect with the thin filaments if they're not even overlapping them? Right? And so that's this idea of a length-tension relationship. There is an optimal length for a sarcomere. Right? You don't have to know the number, right? But you just have to understand this concept. There is a particular length. If the sarcomeres are too long, they're not going to be able to form cross bridges. If the sarcomeres are too short, they're not going to be able to produce any tension because they have nowhere to move. Short enough to allow for a very generous zone of overlap, but long enough so that the thick filaments can still pull the thin filaments inward to produce enough tension, right? And so that's the optimal length of a sarcomere. This is just showing you what happens, right? If we have a too short of a sarcomere, we're not going to produce enough tension. If we have too long of a sarcomere, we won't produce enough tension. Just right. It's like the three bears. The tale of the three sarcomeres. This sarcomere's too short. This sarcomere's too long. Go ahead, Sarah.
Is like one of those like a torn muscle, or like do you actually have muscle?
Yeah. So this could happen in an overstretched muscle, absolutely. A torn muscle would probably just kind of damage and break the protein fibers, and then they'd have to, reestablish themselves. But yeah.
People like they can't move their legs, so it's like they're like too long.
Yeah, absolutely. So botulism can cause some issues with our contractions. So botulism is caused by bacteria, right? The Clostridium botulinum. That's the name of the bacteria. It is a poison, obviously, and it affects your nervous system, your motor neurons specifically. And so this toxin that's secreted and produced from these bacteria actually gets in and it binds at the neuromuscular junction, right? And so what it does is it blocks the release of acetylcholine. Acetylcholine can't come out of your motor neurons. So what does that do to your skeletal muscle if acetylcholine's blocked?
They can't contract.
You can't move. You can't move. They can't contract. Your brain's telling it to move, but it can't, right? So it paralyzes the muscle. It paralyzes the muscle. You can, depending on where and which muscles, this could cause death, right? Again, if those muscles that help your lungs inflate are paralyzed, you can't breathe, right? So the toxin has a very, causes painful muscle spasms. But there's a cosmetic use for it. This toxin is the same thing that's used in Botox injections, right? So if you've ever seen, I'm not judging anyone if you've had them. Some of my friends have had them. I have not. But what they're doing is injecting this into their muscles. Usually they do it in their forehead. And it freezes those muscles up there, right? So that they're not sagging and drooping and whatever. And if you've ever seen someone that's had Botox, like right after they've had it, they look like this. Their eyebrows are really, really tight up there because those muscles are paralyzed. They're literally paralyzing their facial muscles. And so it's just injected with a little small needle to do that. It's also used to treat headaches and things like that. But yeah, I don't know if I would ever inject myself with the poison, but I'm not judging anyone. You know, sometimes you get really desperate to get some help, right? So let's talk about the different types of muscle fibers. We have what we call type 1 and type 2. Type 1 is slow. Type 2 is fast. So, and then we have mixed fibers or intermediate fibers. So sometimes your fibers are one and the other. So to understand the difference between fast and slow fibers, think about a chicken and the fact that your chicken has white meat and dark meat, right? Where is the white meat on a chicken?
In the breast.
In the breast. Where is the dark meat on a chicken?
Everywhere else.
Everywhere else. What does a chicken do with its breast muscles?
Nothing.
Absolutely nothing. What does a chicken do with all the other muscles, the legs and the yeah.
Right.
If you ever watch a chicken, they twitch all over. They're always doing this, right? They're moving, right? Those are the fast twitch muscles. It's dark meat because they have lots of myoglobin. Remember myoglobin? Myoglobin's that pigment that holds oxygen.
Right.
Right? The white fibers are the slow fibers. They're just sitting there. They're not active, right? And so type 1 and type 2 fibers are distributed differently throughout a chicken, obviously, but also throughout us, right? And so we'll talk about where these things are. Type 1 fibers, small in diameter. They're what we call slow fibers. They produce less force, but they produce less force for a longer period of time. So these are our postural muscles. So you don't think about it usually, but your muscles in your back and the muscles in the back of your neck, we learned the splenius capitis last night in lab, it's contracted all the time, holding your head up, holding your back up, right? Those muscles have to be slow twitch fibers, or else you would build up so much lactic acid in them you wouldn't be able to get through your morning routine, okay? So the muscle fibers that hold you up, your abdominal muscles, your back muscles, your neck muscles, those are slow twitch fibers, right? So they rely on oxidative catabolism, right? They rely on that ATP being created from the oxidative phosphorylation of glucose, right? Breaking down glucose, using oxygen, producing lots of ATP, right? They rely on mitochondria. They rely on myoglobin. Type 2 fibers, these are fast fibers. These are ones that will rely on glycolytic catabolism. These burn out quickly. These are the ones that are more apt to fatigue. They have fewer mitochondria because they're not using them, right? They're doing glycolytic catabolism. They're just lactic acid, right? Creating lactic acid. They have a less extensive blood supply. So these are those white fibers, right? And so these fibers are pretty much everywhere else. But even within individuals, you might have a range of fibers throughout your body. So for instance, think of, I was on the high school track team. I was a distance runner. And I even today, without training, I haven't ran in a couple of months, but I could probably go out there and bust 6 to 8 miles out. It wouldn't be pretty, but I could do it. Because I have lots and lots of slow fibers in my legs. I know I can do it. But you know what? I could race any of you to the parking lot and I would lose because I am a slow runner. I'm just not fast. But going back to the high school track team, there were some dudes and girls on the track team that were so fast. They didn't even train. They would joke around, they would go party on the weekends, but they were so fast. because the fibers in their legs were predisposed to be fast twitch fibers. So everyone's body composition is put together a little differently to predispose you for either endurance type things or sprinty type things. But also throughout your body, right? Your back muscles tend to be those slow twitch. Your wrist muscles, as I know lots of you are writing frantically throughout lecture, you probably have to say, oof, my hand hurts, right? That's because they're fast twitch muscles, right? So, all right. Type 2 fibers can be fast oxidative glycolytic or fast glycolytic. So they can be broken down even more, right? They can be intermediate or very, very, very fast. So intermediate would be kind of in between, right? Whereas fast glycolytic, those guys, powerful twitches, lots of tension. They expend their energy very, very quickly. So again, I'm thinking of lots of hand, lots of feet. There's this ride. Have any of you guys ever been in Disney World? Best ride in Hollywood Studios is the Buzz and Woody ride. I forget, Toy Story Mania, I think is what it's called. But it's this game ride, and it sounds weird, and the motion looks weird when I tell you, but you're pulling this string, and you're basically, you wear these 3D glasses, you're pulling this string, and you're firing this like cannon at these little things, and Buzz and Woody are like cheering you on, and it's super fun, right? You know what I'm talking about? It is like the best game. Okay, but when you're done, your arm hurts you so bad, because you're going like this to try to fire off those little cannons. So, and we got on it like 3 times in a row because there wasn't a wait, so there wasn't a lot of time, and I'm not kidding. Yeah. Oh.
Because it was like noon.
Yeah. Yeah. I've waited 3 hours for it, and I've waited 30 seconds for it. I think it depends on when you go.
Because like when I went back the second time, we had to leave there.
Yeah, we didn't have anything else to do. We were like, we had already ridden all the rides, and the kids were already sleeping, so we're like, we'll just stay in the line, and by the time we get to the front, they'll wake up, and yeah. We're Disney people. We go to Disney all the time. I don't like wear Mickey Mouse clothes or like have princess dresses, but I just enjoy the Disney parks. They're really fun. Anyways, all right. So we're talking about different classes of skeletal muscle fibers here. So just kind of thinking about where these muscles are in the body. A baseball player, right, sitting in the dugout. He's using primarily type 1 fibers in his back and his abdomen, right, sitting upright. But when the player gets up and jogs to bat, type 2A, those intermediate fibers, right? But when he hits the ball, lots of power, really hard, really fast, right? That's 2B. You can't swing that bat repeatedly, time and time again, without getting fatigued. You know this if you've ever been to a batting cage, right? It's tiring and exhausting. So this is looking at a cross-section of an actual muscle, so you can see that literally all of our muscle groups are mixes of these dark and light fibers. Go ahead, Lucy.
Does everyone have all 3 types?
Yeah, just in different proportions. Yeah. Even though I'm really slow, I know I got some fast fibers in there somewhere. All right, and this is just showing you some of the different properties, right, comparing and contrasting the 3 types. Let's talk about motor units. Okay, so picture this. I'm going to lift this desk up above my head, right? And when I go to do it, I try to lift, actually I'll just use this. I'll pretend like this is really heavy. Okay. I'm gonna lift this umbrella up above my head. And in order to do it, I have to start by picking it up first, but it's really heavy. And when you first try to pick up something heavy, not all of your muscle fibers contract all at once, right? So remember, one motor neuron coming down from your brain or spinal cord controls a bunch of motor fibers, right? A bunch of muscle fibers. And so one motor neuron might say, you know what, that's probably really light. Nope, it's not. We're not contracting enough. We're not producing enough tension. Let's recruit some more muscle fibers. We still not produce enough tension. It's still too heavy for us. Motor units are different patterns of muscle fibers that can be recruited to produce more tension. So by the time I figure out, yes, I can lift it up, by the time I can do that, I've recruited the majority of my muscles in my arm. Get it? At first, not many are flexing, not many are contracting. Your body tries to get away with producing as little tension as possible. But as your body's trying to do so, this is why it takes you a little bit of time if you've ever done weightlifting, or maybe you're trying to pick up a couch or whatever you're moving. You feel it at first, you're like, and then eventually you can do it, right? It takes a little bit of time for your nervous system to figure out exactly how many muscle fibers need to be recruited to get the job done. And your muscle fibers work in what's called a motor unit. So in a muscle, like your biceps muscle, right, this one, there's probably 10 or 15 motor units. And at any given time, to lift something like the umbrella, you could probably get away with only having one motor unit, right, because it's so light. But if you're going to lift up a table, lift up a toddler, right, lift up a big glass of wine after class, right, you might have to recruit more motor units to move that, to produce enough tension. So when a motor neuron fires an action potential, all of the muscle fibers in that motor unit respond. So you might need more neurons to fire to get more motor units to be, oh no, it was so good. We haven't had any problems with it in a while. I think I deduced it from my other class that it's someone around here that is using like some infrared something, yeah, and it interferes with it. Okay, so the number of fibers in a motor unit is going to vary depending on what the motor unit does or what the muscles do. Just trying to get this over here. It messes with the mouse too, see what I mean? Like I keep trying to put the mouse over there. I'm doing a little experiment here to see. Yeah, it's totally just the projector because it works fine now. Okay, let's turn it back on. All right. So the number of fibers in a motor unit is going to depend on the function of that motor unit, what that motor unit does, what muscles it's innervating, where it is in the body, what the function of that overall thing is. Right. This will just warm up in a second. So there's a couple good analogies to get you to think about how these things work. Again, at the initiation of a motor command, your body tries to get away with using as little motor units as possible, right? It wants to expend as little energy as possible, so it's going to use a low number of motor units. But as your body realizes you're going to need more tension, right, it has to recruit more and more motor units. Now this thing's spazzing out and not projecting. Yay! Oh, it's coming. Okay. I'm impatient. All right. Muscle tone is the idea that what we have is a resting level of contraction. When you think of someone who is toned, right? Or when you say, I don't want to bulk up, I just want to get toned. What you're really saying is, I want it to look like I have muscles even when I'm not contracting them, right? That's what toned means, right? And literally, that's what it is. Your muscles are contracted slightly without you even have to do it, right? You don't even have to think, I'm going to contract my biceps right now. I'm going to look stacked, right? You don't have to do that. They're naturally like that because they're toned, right? So getting toned means you're getting your muscles prepped and ready to develop a lot of tension, to produce a lot of tension, to contract. So your muscles, instead of like laying around like, yeah, bro, this is cool, right? Your muscles are sitting around like, okay, I know we're gonna have to contract soon. I know we're gonna have, they're sitting around and they're excited, right? People who have greater muscle tone burn more calories because they're using more ATP because their muscles are like, okay, we're gonna contract soon. I just know we're gonna, they're already excited to some level, right? Muscle tone is vital for your body. You have to have some degree of muscle tone, otherwise you're literally a vegetable in bed, right? You have no control over your muscles. You have to have it to stabilize your joints. You have to have it to keep you erect and keep you upright, right? So you might not look like you're toned, but your back muscles work, right? Your back muscles are toned and keeping you upright, right? Your shoulder's stable, that joint's held together, your hip stable, your knee stable, all your joints are held together, right? So there's varying levels of tone, but getting toned is really a thing, and it really does change the physiology of how your muscles work. Preparing them by exercising, getting them ready to produce lots of tension, keeps them ready to produce lots of tension, right? Which keeps them in this resting level of contraction, this idea of being toned. And in staying toned, what your nervous system is doing is it's alternating which motor units are contracting, right? That's what, so while I said your muscles are sitting around like ready, they're excited, but from the big picture, different fibers are excited at different times. Different motor units are being recruited at different times. If the end result is the same tension across the muscle, it might help if we kind of look at it like this, right? So let's say we have a blue motor unit and a red motor unit. We'll just simplify and say there's only two, right? If you're toned, maybe 1 millisecond, the red ones are contracted, the next millisecond, the blue ones are contracted to give the red ones a chance to rest, right? They're alternating which motor units are going to stay slightly contracted to produce this level of tone. So that brings us to the idea that not all contractions are the same either. So we've learned that not all muscle contractions are the same, right? We have this idea of twitch and summation and tetanus, right? Not all muscle fibers are the same. We have fast and slow and intermediate. But even the types of muscle contractions, how the muscle actually moves, can be different. We have isotonic contractions and isometric contractions. And if you've ever done any type of weight training before, you probably already know these. You just maybe didn't put the vocabulary to them. So an isotonic contraction has two parts to it. There's a concentric contraction and an eccentric contraction with every movement. Okay, so I'll have my dumbbells here, my erasers. All right, an isotonic concentric contraction. Isotonic means that the muscle is changing in length. The muscle is actually shortening, right? The constant tension while the muscle shortens is the concentric. So if we're talking about moving the biceps, the concentric contraction is this, right? But again, if you've ever been to the gym, you know some people go like that after they lift it up, right? They're missing half of the movement. The other part of the contraction is the eccentric contraction. The eccentric contraction is the reverse. Concentric, eccentric. Concentric, eccentric. Think about a push-up, right? It's just as important to control your body on the way down to the ground as it is to push yourself back up, right? Concentric, actually this is eccentric. This is concentric. With a push-up, it's backwards because it's your extensors. Isometric contractions are the opposite. So with isotonic contractions, you're shortening the muscle. The muscles are changing length. There's movement going on. But I can contract my muscles without moving them at all. You can too. Do it. Contract something. No one will know. Right? You can do it. You can contract anything on your body, and no one would know. Maybe your face. Your face is hard to contract without people knowing it. Isometric contractions are ones where you contract but you don't change the length. Right? So you can do isometric contractions all the time. Just squeeze. I think of those like old school workout videos that my mom used to do when like the ladies are like laying on the floor and they're like squeezing their butts and like and squeeze, like squeeze, and squeeze. They're wearing like leotards. All right, just kidding. My mom didn't do them. I did them. I've been doing workout videos since I was like 5. I don't know. I love working out. Anyways, all right. You wouldn't know it by looking at me, but that's okay. Isotonic contractions. Concentric, eccentric, isometric contractions. Right? Isotonic, concentric, eccentric, isometric. All right. And this is something else, you know, if you've ever done a workout routine. You know about DOMS, right? Delayed onset muscle soreness. You work out, right? You're super pumped, you feel great later in the day. You're like, yeah, you might feel a little jello-like, especially if it's been a while since you worked out, but the next day, or sometimes it's even 2 days later, that's when the soreness really kicks in. It's called delayed onset muscle soreness, and it's a real thing. So this is the soreness that follows exercise, right? And it's due to the accumulation of that lactic acid. Remember, lactic acid builds up in your muscles because of that glycolytic catabolism. It's actually due to these little tiny micro tears. What's happening as these sarcomeres are contracting and contracting and contracting and they're kind of wearing out, right? If you work out and your body's not used to it, these proteins can actually kind of fall apart a little bit. The sarcomeres can kind of fall apart, produce these little things called micro tears, right? And you put lactic acid on top of it, right, which is going to cause even more damage. And so your body needs time to heal itself. The best thing to do with the soreness is drink water. That water is going to flush out all that acid. It's going to help get all of that out of your tissues and help make you feel a lot better. Water is key. So effective DOMS treatment is actually doing more exercise, right, and drinking lots and lots of water. There's also massage and things like that to help move the lactic acid up, depending on where the burning sensation is, where you're sore. Massage can really help because what massage does is it pulls, let's say, your wrist really hurt you or whatever. Massage is actually pulling that extra lactic acid from wherever it is, right, pulling it back towards the heart, putting it back into your venous system so that your kidneys can flush it out. So that's the whole kind of theory behind massage, is getting those lymphatics, and a lot of you love lymphatics, getting those lymphatics moving so that those things that are sitting around and kind of festering can get back into circulation. So there's topical treatments and things like that too, but really water, massage, and rest. So physical therapy and physical training can help you build something called myoplasticity. Myoplasticity is the change in muscle structure. So this is your actual muscles changing over time. Again, if you've done a workout routine, you know this happens, right? The majority of our skeletal muscle fibers are amitotic, so they themselves are not divided. You don't get more muscle fibers, but you get more myofibrils. So if you remember my box of spaghetti analogy, right? A muscle fiber is like a box of spaghetti. The spaghetti noodles are all of the myofibrils. So just imagine pushing more myofibrils into your box, right? And your box is going to have to get bigger. That's how your muscles grow, by gaining more and more myofibrils. The muscle cells themselves don't really divide. They can under emergencies. So there's special satellite cells. They're kind of like stem cells that can produce new muscle tissue if maybe the area is damaged. So like I told you guys how I had my shoulder surgery and I don't really have an anterior deltoid muscle. When we do muscles, I'll show you. It's really deformed. Slowly over the past 4 years though, it's growing back. I have more of it now than I did before, but that's one of the reasons I don't have a good range of motion. I have no muscle there to do that motion, right? And it takes a while for those cells to kind of repair and replace. So myoplasticity is the changes because of the training, right? And this can vary depending on the type of training that you're doing. Endurance training, right? Do you go to the gym and you're just on the elliptical, ride the bike, go for a walk, go for a run? Or are you doing resistance training, right, with your concentric and eccentric contractions, maybe some weight training, planking, those types of things, right? That's going to determine how those muscles change and which muscles change. So, I don't know what I just did. There we go. Okay, let's talk about endurance training. So, how many of you have ever done endurance training? All right, I'm an endurance trainer, former. Does anyone run a marathon or a half marathon? Well, I feel the itch coming on that I need to run. I haven't ran a race in like 2 years, and I feel like I need to. So I might start like tomorrow. I don't know. All right. I'm impulsive. All right. Endurance training is when you do a large frequency, a high frequency of things, right? So lots of reps, lots of walking, right? Lots of running, a repetitive motion time and time again. What this is going to do is it's mostly biochemical changes in your body. Your body's going to be more efficient with endurance training. So it increases the enzymes that are there for metabolism. Your body's saying, oh, we're doing lots of this metabolism. We better go ahead and make more enzymes so we can do this metabolism even better, right? It's going to increase your fatigue resistance. So you're going to become better at doing things longer because you're doing things longer in this repetitive movement, in this repetitive exercise. You're going to be more efficient at using fatty acids for metabolism. Your body's going to say, you know what? I go through that glucose so fast, I need to figure out how to use these high energy fatty acids to get energy because I'm going to run out of glucose if she keeps this up, right? And it also increases the vasculature. It gets your blood really efficient at pumping and gets your tissues really good at pulling oxygen out of your blood, right? So it's mostly biochemical changes that take place with endurance training. With resistance training and strength training, this is where it's a minor changes in the biochemical, right? So your body is going to get better and more efficient and those things, right? But it's going to increase in myofibrils. The anatomical changes are much more drastic with resistance training. The number of myofibrils increases. We call this hypertrophy, right? Hypertrophy is cell growth. Your muscles undergo hypertrophy. You bulk up. That's hypertrophy. So, resistance and strength training with hypertrophy actually becomes decreased amounts of mitochondria, right? Decreased blood supply to the muscle fibers. So you're almost training your muscle fibers to become fast twitch, right? Because they're getting bigger, so the ratio of mitochondria to cell space decreases, right? So you have less mitochondria for the size of the cell, right? And because that they're filling with myofibrils, they're also not as much blood flowing to them, right? So by default, you're kind of converting them into fast twitch, right? So this can actually decrease your endurance, right? Again, going back to maybe weight training class or any other exercise class you may have had in the past, you would notice this, which is why both types of training is recommended. I can speak from experience though. I know that when I weight train as opposed to just endurance train, my running is way better. So there's probably because I have mostly endurance fibers, but I feel like when I just do strength training, even if I only run once a week, I can run much better if I only do that instead of running a lot. But I think that also has to do with nutrition, because when you run a lot or exercise like endurance train, your nutrition needs to be on point. And I eat a bag full of ginger candies. I was telling some people before class, I'm not a good eater, so. Were you going to say something there? No? Okay. All right. So, other changes due to physical training. Disuse. You're doing it wrong, right? Or maybe you're not doing anything, right? This is going to decrease, right? This is going to decrease your myofibrils. It's the use it or lose it. Same thing that we had in bones, we have it here in muscles. You don't use it, you're going to lose it. And so you need to do something physical to keep your muscles up. You need to do something physical to keep your bones up. And guess what? In our next unit, which is the nervous system, you got to keep your mentalness going. I say mentalness like tongue-in-cheek. I don't mean like craziness. I mean like keep your brain active, right? You need to keep your brain active if you want to keep your brain active. So this is just a diagram showing those changes, that idea of hypertrophy, more myofibrils getting packed into that muscle fiber, right? Or more mitochondria from endurance training. Our muscles can fatigue, though. We mentioned the delayed onset muscle soreness from the lactic acid buildup, but muscle fatigue also has to do with the depletion of your ATP reserves, your oxygen reserves, your myoglobin reserves. And so typically what you'll see after exercise is increased respiration rate for a while so that your body can replenish the amount of oxygen that was depleted, right? So it's called oxygen debt. The oxygen debt that you accrue after a workout, after an endurance, or even after physical training, right? Your body has to breathe heavily afterwards. Again, you know this. Just because you stop running doesn't mean you're breathing stops. You continue to breathe heavy afterwards, right? Sweating, bringing your body temperature back down, all parts, showing you that your muscles are fatiguing, right? That excess post-exercise oxygen consumption is there to replace that oxygen debt and get your body back up to its oxygen capacity. It allows your body to recover from any imbalances that may have happened, because while you're exercising, most of your blood flow is going to your muscles, which means things like your digestive system aren't getting the oxygen that they need, right? So once you stop exercising, breathing heavily allows you to not only replace the oxygen that you used up in your muscles, but get the oxygen going back to your digestive system, your urinary system, your reproductive system, the things that weren't active while you were exercising. So that was all skeletal muscle that we were talking about. Let's pay some homage to smooth muscle. I'm going to try to go full screen because I think it's, now that I tested my hypothesis of it's the screen and I just restarted it, I think I don't think it'll cause us any problems. So let's talk about smooth muscle. So smooth muscle is in our hollow organs. Remember some of the basic differences between skeletal muscle and smooth muscle, right? There's no striations, it's involuntary, there's only one nucleus, they are spindle-shaped, right? And they're found in the walls of hollow organs like our blood vessels, our respiratory passageways, they're found in our bladder, our urinary bladder, in our reproductive tract, in our digestive tract. So basically anywhere that's not the heart or a skeletal muscle is smooth muscle. All right, the little hairs, the erector pili muscles on our hairs, that's smooth muscle. Okay, so they can form sphincters. Sphincters are circular openings that are muscles that guard entrances to the body. We learned a sphincter last night. What's it called? Orbicularis. Oris. That's okay. We had a bone practical right beforehand. I don't blame you. Orbicularis oris is a sphincter muscle, right? It controls the opening to your mouth, right? So smooth muscle cells have actin and myosin, same way, but they're not arranged in a sarcomere, right? The striations, if you remember, are because of these alternating patterns of thick and thin filaments, which create this striped appearance. Well, our smooth muscle is not striated, so there's no pattern to the thick and thin filaments. In fact, the actin filaments are arranged in something called a dense body. So it kind of looks like this inside our smooth muscle, which is kind of spindle-shaped. You'll have a dense body. Right? And then there's some random thick filaments. And so when the muscle wants to contract, it just kind of grabs onto anything that's there and pulls. It's not this very succinct, organized contraction where it's shortening. This cell is going to contract kind of like a blob, right? Almost like squeezing a water balloon together, right? It gets like thicker and fatter, right? That's kind of how this is going to be when it contracts. And these little circles, they look like an asterisk, right? Those are actin centered around a dense body. The myosin's just kind of haphazardly throughout. There's lots of intermediate filaments, part of the cytoskeleton, holding everything together, keeping everything in place.
The actin is the dot?
Yeah, so the black thing is called a dense body.
Oh, okay.
And coming off of it, these little like wings
Those are actin.
is the actin, yeah. The red is the myosin. So remember, the refractory period is a lot longer in smooth muscle. The myosin heads actually, are randomly placed. It's very haphazard. There's no motor end plate. So the organization of smooth muscle is not quite the same as with skeletal muscle. So you can see, this is kind of maybe a better drawing, I don't know. But the idea is it's spindle shaped, and when it contracts, it kind of smushes like a blob instead of just a nice shortening. It's more blob-like. And that blob-like contraction kind of allows for this wave-like movement when the whole organ contracts. When the whole organ contracts, it's going to contract in kind of a wave-like pattern instead of just a basic shortening like our skeletal muscle does.
And that would be to move stuff through.
Yeah, right. So to help propel food through your digestive tract, propel urine through your, to your
Because if you
ureters, to
move
your
all at
bladder.
one time,
Yeah,
it
yeah,
would just
exactly.
squish everything.
Yeah, everything will get squished. This smooth muscle is also there to help dilate and constrict your blood vessels and dilate and constrict your respiratory passageways. So it comes in handy. So it involves a cascade of events. It's very different from our skeletal muscle. The calcium ions come from the outside, so there's no sarcoplasmic reticulum releasing it. Those calcium ions come from the extracellular environment, and that is going to activate an enzyme called MLCK. That MLCK turns on ATPase, and that ATPase triggers the cross bridge forming, right? That attachment of the myosin head, the power stroke, the relaxation. All of that happens the same. The calcium comes in, that's different. The kinase enzyme is different. The ATPase enzyme is different. Everything else is the same. Repeated contractions help change that shape from thick to thin, right? Kind of fat and globular. Helps move in like a wave-like pattern. It can contract up to 80% of its resting length. So this can really smush, as opposed to our skeletal muscle, which doesn't move a whole lot, right? Doesn't require as much ATP either. But it does require some ATP. So even the act of digesting uses energy, which is kind of cool, I think. The relaxation occurs when the calcium's pumped back out, right? Those enzymes, MLCK and the ATPase, become deactivated. There's something called a latch state. The latch state is the alternative to relaxation. So this is when the cell kind of maintains its semi-contracted state. This is really important for like sphincters, right? So when the sphincter contracts, you don't want it to contract and then open back up, right? You want it to stay closed. So, I mean, think about where all the sphincters are in your body. You kind of want them to stay closed, most of them, right? And so that's that idea of the latch state. They can kind of lock, close. And then the different motor units will alternate to help keep it contracted as a whole. Contracts as that globby shape. So a single unit of smooth muscle, this is, again, all of our hollow organs. They're linked by gap junctions so they can communicate to each other, kind of like our cardiac muscle that we'll see. And they can respond to multiple stimuli, which is important because smooth muscle is not just controlled by our nervous system. Smooth muscle can be controlled through hormones. Smooth muscle can be controlled through local communication. Oh, he's contracting. Okay, I'm going to contract now, right? They can coordinate their contractions through those gap junctions, and they can respond to more than just one stimulus. So even if your nervous system is saying, I'm not hungry right now, I'm not hungry right now, your hormone system can say, yes you are, right? And make your stomach start churning. So there's also multi-unit smooth muscle. This is less common. So this is where there's individual cells that operate independently. These are usually related to nerves, so like the root hair plexus and the erector pili muscles of our integumentary system would be an example of that. I think that was me this time. Yeah. Okay, cardiac muscle. Shorter muscles, they're branched, as opposed to our skeletal muscle, which are long fibers. Smooth muscle, spindle shape. Here we do have usually just one nuclei, sometimes there's two. There are striations, so you have that same organizational pattern in cardiac muscle, right? But we have intercalated discs here. These are special junctions in between the cardiac muscle cells that kind of link them together. They're specialized gap junctions that help them coordinate their contraction. And this is a good thing because you don't just want